18.2 Convex and Concave Lenses. The last section in Chapter 18, we'll have a test on Chapter 7 and 18 in a couple days here, so be ready to rock and roll. We have focused on convex and concave mirrors, and now we're focused on lenses. And really, what's the difference? If you have mastered convex and concave mirrors, nothing really changes from for lenses except a couple things. And here are a couple things. Well, first off, what is a lens? If we're dealing with refraction, a lens is just a piece of material such as plastic or glass that is used to focus light to form an image. So glasses, obviously glasses that many of you wear is a good example of a lens. Now, when we talk about convex lens, a convex lens is thicker at the center than it is at the edges. So your typical convex lens is going to look like this. And your typical concave lens is going to look like that. It's skinnier in the middle than it is at the edges. And a concave lens is always going to have diverging light, where a convex lens is going to have converging light. Now, a couple of other things here when we talk about lenses. First things first, our equations are going to stay the same. Our 1 over f is equal to 1 over di plus 1 over do. And our magnification is equal to hi over ho, which is equal to negative di over do. A couple differences, though, when we talk about real and virtual images. Remember, with mirrors, a real image happened on the front side of a mirror, and a virtual image happened on the back side. Now that flip-flops when we go to lenses, because the light is supposed to pass through a lens. So a real image on a lens is on behind the lens, and a virtual image is in front of the lens. Now, one thing to clarify too, remember when we have a virtual image, the distance is negative. So if we have a negative distance for our image in any lens, that means the image is being formed in front of the lens. So this kind of summarizes what we just talked about. When we're using the equations for lenses, virtual images are on the same side as the object, so they're in front of the lens. A negative magnification or a negative height, again, means that it's just inverted. Concave lenses only produce virtual images, and convex can produce both real and virtual. We are not going to go into as much detail with the light ray diagrams as we did with mirrors, simply because you get most of the practice with mirrors and lenses don't really change too much. So if we take a look at a convex lens, what we have here is we're going to do the same drawing that we did before. We would have the initial line off the bottom of the arrow, which I will do in black. It's going to come, hit. Now this is a lens. If this was a mirror, what would happen? This would bounce straight back. But for a lens, this is going to continue to pass through. All right. Our next line, which I'll do in red, again, from the top of the arrow to the mirror. If this was a mirror, it would bounce off. It would bounce off in this direction. But since it's a lens, that light is going to pass through. And when it passes through, we're going to follow it, and that light's going to go down at an angle as such. Then our third line, which I'll do in purple, would go, typically if this was a mirror, it would go off the top of the arrow, through the focal point, hit the mirror. Now, or the lens. If this was a mirror, this light ray would bounce back. But since this is a lens, our light ray is going to go through the piece of light. They're going to meet. Where they meet is right here. So this is our new image. Same thing, we're using the mirror principles, except remember with lenses, the light travels through the lens. All right, light travels through the lens. So this is an example of a real image. It's on the back side of the lens because light is traveling through. So that's kind of an example. Now, convex lenses, if the object is at the focal point, you won't be able to see an image, so it'll black out the image. And also, when the object is closer to the lens, the rays will diverge on the opposite side of the mirror, and you will get a virtual upright larger image. Don't necessarily worry about that as much as just basically, if you can understand the basic light ray diagram for a convex lens, for anything outside the focal length for a lens will be good to go. So this is a convex lens. If we take a peek at a diverging light, which occurs in a concave lens. All right, what we have is the same thing here. We're going to draw our arrows. Well, what we would have immediately is the black. I'm going to do in black. If this was a mirror, this would bounce straight off and head back. But since it's a lens, our lens is going to travel through. Our light will travel through. Next up, I'll do it in red. What we would have is, if this was a mirror, again, we're going from the top to the mirror or the lens. If this was a mirror, the light would bounce back like this through the focal point. But since this is not a mirror, it's a lens, what we see is this light would continue traveling like this. We do again our third line in purple from the top of the arrow through what would essentially be the focal point of a mirror. But since we're dealing with lenses such as this would hit. And if this was a mirror, this would come back like that. Since this is a lens, however, the light is going to keep traveling like this. Now, one thing that you can see from a lens perspective in a concave lens is, will that red line and that purple line on the back side here ever meet? No, they are diverging. So what happens is the concave lens is very similar to our mirror drawing in regards to our image is going to form on the front side of the lens. Therefore, our image is virtual. Therefore, our DI has a negative value. So for a concave lens, a couple refreshers. The light rays are always diverging. F should be given as negative because the focal length is on the front side of the mirror. DI will always be negative because the object is always virtual. And DO will always be positive because it's still on the front side of the lens. So a couple pieces of information to help apply when you're dealing with concave lenses when you are doing problems. So if we refresh here, an object is placed at 32 centimeters from a convex lens that has a focal point of 8 centimeters. Where is the image located? If the original object was 3.0 centimeters tall, how tall is the image? So again, we're going to do our magnification equation, the 1 over f is equal to 1 over di plus 1 over do. We have do as being 32.0 centimeters. We have our focal length, which is positive because we have a convex lens at 8.0 centimeters. And what it's asking for is where's the object? We're looking for di and we're looking for hi. So if we go ahead and plug it in, 1 over f is equal to 1 over di plus 1 over do. Let's go ahead and plug in. We have 1 over 8 is equal to 1 over 32 plus 1 over di. When you solve for di, you end up getting an answer of 10.7 centimeters. You go 1 divided by 1/8 minus 1/32. So we got di. Next up, we want to solve for hi. Well, remember, hi divided by ho is equal to negative di over do. We go ahead and plug in. We're solving for hi. Ho, the height of the object, it tells us in the question the original object was 3 centimeters tall. 3.0 is equal to negative di. Well, di was 10.7, so now it's negative 10.7 divided by do, which is 32. We cross multiply, and we solve for hi, and hi ends up being negative 1.0 centimeters, which tells us a couple pieces of information. Actually, it tells us that the image is inverted. So you might have to draw a light ray diagram for that if you want to as additional practice, but you don't have to. All right. Last couple things on lenses here. We have a couple terms to talk about. Spherical aberration is where lenses don't focus all parallel rays at one spot, but the rays are approximately close. So what we essentially have here is we have a lens. And this may happen if you have glasses and it's scratched. Ideally on a lens, my focal point's right here. I have a light ray come through, boom, another one come through, boom, another one come through, boom, another one come through, boom. They perfectly meet at the focal point. When you have spherical aberration, what it does is it's going to adjust your focal point a little bit for each light ray. That's going to throw it off. So if our light ray's here, we might have one come in like this. We have one come in like this. We might have one come in like that, and another one come in like that. And what you see is you don't really have a clear focal point. What happens is that results in a fuzzy object. Your eyes tend to do this if you are nearsighted or farsighted. They don't necessarily focus at the exact point, and your focus isn't always necessarily clear. So that is spherical aberration. Chromatic aberration is lights focused on different points, causing it to be viewed ringed in color. So a lens is similar to a prism, so light is refracted at different angles. So anytime you have chromatic aberration, it's going to be ringed in color just because the light is being bent very slightly in comparison to what it should be. And lastly, this may happen with an achromatic lens. It's two or more lenses. It reduces chromatic aberration. If light travels through more than two lenses, it's really going to reduce that amount of error that can occur in chromatic aberration. So that concludes section 18.2 on lenses. You'll have some questions on light ray diagrams for lenses along with magnification, DI, DO, and focal length questions as well on 18.2 tomorrow.